After discussing function minimization using kernel map, whether it's 2 variable, 3 variable, or 4 variables, now we will see some features of special functions. And if we can, we show its relation to the kernel map. So the odd and even function, on K-map form checkerboard patterns, like the chess game. The ones of an odd function correspond to the minterm having an index with an odd number of ones. The ones of an even function correspond to minterms having an index with an even number of ones. You can see here the XOR, which is an even function, form this pattern, and you can see that it's like a chess game. Similarly, for the XNOR, the difference between them, the XOR start with 0 here, and the XNOR start with 1. Again, I'm reminding you the way to fill it is 0, 1, 1, 0, and so on. So the moment you see this pattern, you know for sure it's an XOR function of 4 variables. The implementation of an odd and even function for greater than 4 variables as a 2-level circuit is kind of difficult, so we use trees made of 2 inputs XOR or XNORs, 3 or 4 inputs odd or even function to generate higher the number of inputs of their variables. The high impedance output, the logic gates introduced thus far have either 0 or 1 as an output values. They cannot have their outputs connected together. And they transmit signals on connections in only one direction. The 3-state or tri-state logic adds a third logic value. So we have 0 and we have 1, and now we are introducing a high impedance, or the way we denote it is high Z, or sometimes we denote it as Z. What is this high Z value? The high Z value behaves as an open circuit or as a floating connection. This means that looking back into the circuit, the output appears to be disconnected. One of these gates is the 3-state buffer or the tri-state buffer. For the sample and the truth table, the IN or N is the data input. The EN is the control input for enabling the 3-state buffer. As you can see here in the sample, this is the input and this is the output, and you have this third terminal, which is enabling if there is a connection between the input and the output, or there is no connection between the input and the output. So for when the enable is equal to 0, regardless of the value of the input, denoted by X, which means don't care, the output is going to be high impedance. Because the enable here is 0, there is no connection between the input and the output. And the output, when you look at the output, you will see that it's not 0 and it's not 1. It's disconnected completely. So it's going to be high impedance. And when the enable is equal to 1, the output value follows the input value, which means the buffer works normally. When the enable is equal to 1, the buffer works normally. When the input is 0, the output is 0. When the input is 1, the output is going to be 1. There are some variations. The data input N can be inverted. The control input, the enable, can also be inverted, meaning it was going to be an active low. The input is the same. And this is happening by the addition of the bubbles as I showed you. The three-state logic circuit. Now the data selection happens as follows. You will have a terminal S. You can consider it as an input. This S, when it's 0, the output will select or choose one of the inputs. When it is equal to 1, the output will choose the other input. So S for selection or for the selector. If we consider S is equal to 0, after the inverse is going to be 1, and here it will be 0. Because this is 0, there is no connection here, and this one will make the connection between the input and the output. And in this case, the input N0 will be shown in the output line. If you consider the other value of S, when S is equal to 1, after the inverter, it will be 0 here, and here it's going to be 1, which means there is no connection here, and the connection is over here. So the input N1 will show into, or you can see it in the output line. To show this behavior in a table or a truth table, you have the N0 or N1, which is these two lines. They are tightly connected to S. When S is equal to 1, the output line will be N1. And when the selector S is 0, regardless of the value of the input 1, the output will be the value of N0. You can see that those don't care, meaning that you don't consider the input in N0 when the S is equal to 1. So it doesn't mean anything to you. The output line will be input 1. And when it is 0, those don't care. Tells you that regardless of the input N1, the output line will be input 0. Now, there is another case that is not shown in this diagram. If S is equal to 0, meaning if the enable 1 is equal to 0, and also enable 0 is equal to 0. And in this case, 0, 0 here means that there is no connection here, there is no connection here, and the output line will be floating or high Z. One of the two buffers output, in this case, in this diagram, we are forcing the output line to be connected to 1 and exactly 1 of the input. So the last row of the table never occurs in this block diagram. As an exercise, if we were asked to implement a gate with two three-state buffer or two tri-state buffers and two inverters that have this function, which is the XOR. X XOR Y, which you know that it's X bar Y or XY bar. So to do this, you can have the truth table like this. If you say that this is X and this is Y, and the function is XOR, Just to match the same block diagram in the slide, I will switch the X and Y. And you know the XOR is commutative. Now the output in the XOR is, if they match, it's going to be 0. If they differ, it's going to be 1. To design using two tri-state buffers, you divide the truth table into 2 to make it easier for you to understand. And you will consider one of the input as the selector S. In this case, we will select the Y to be the selector. Now, Y is the selector. So invert it, it will connect to one of the tri-state buffer, and it will be connected to the other one directly. What happens now, you know if the Y is equal to 0, the relation between the output and the input X is the same. So the output will be exactly X when Y is equal to 0. So when Y is equal to 0, meaning after the inverter, so when it is 0, after the inverter, it will be 1. So this one is active. The output line, or F in this case, will be X. You will get X. So now we finished the upper half of this gate. The lower half, when the selector line Y is equal to 1, when it is 1, this one will be active. And here, when it is 1, after the inverter, it's going to be 0. So this is not active. And here, this one is active. It's enabled because it's 1. And now, what goes to the output is you check the relation between this input and this output, and you can see that there is an inversion between the input and X. So we say that F in this case is equal to X bar. So you take X, you generate X bar by adding this inverter to get the X bar or X prime, and it will be chosen in the output line. This is actually a famous method of design called a design by mux or design by multiplexer, and we will see it in detail later when we talk about multiplexers. After we see some of these gates now, the first gate being the XOR and XNOR, and the second gate being the tri-state buffer. Now, the tri-state buffer, we show it in this set of slides because it shows you a simple and easy design for circuits that even have a third output, which is the high impedance. Now we will check the multiple level optimization. The multiple level circuits are circuits that are not two level. Usually the two levels, the first level will be the number of ants, and the last level is a single big or vice versa. So it's either going to be with or without the input inverter, or with or without output inverters. The multiple level circuits can have reduced gate input cost compared to the two level SOP and BOS circuits. The multiple level optimization is performed by applying transformation to a circuit represented by equation while evaluating the cost. Meaning, starting from a certain two-level circuit, you will try to reduce the cost even further by using some manipulations to reduce the number, for example, the number of literals. So let's see it in this example. If you have G is equal to ABC or ABD or E or ACF or ADF. Now, this is a two-level circuit because it's a sum of products. So you have the first level and the last level is OR. For example, this and is going to be ABC, A, B, and then C. You will do it for the other terms, and then you will collect them all in an OR gate. Now, the gate input cost here is equal to 17 because you can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then you add the terms. We have 4 terms to get the gate input cost. Now, you can notice that you can take some common factors here. If you take AB as a common factor, you will end up with C or D. If you take the common factor here, AF, so you will end up with C or D. And because of this manipulation, because we are using Boolean algebra here, now it's no longer a two-level circuit. It's a multiple level circuit. And if you try to get the cost, you will find that you reduce the cost from 17 to 13. You can also apply more Boolean algebraic manipulation or Boolean algebraic laws to reduce this cost even further. So you can see here that you are generating C or D in both of them. So what happens is we will share this C or D. So we will get C or D first and then share it between the two ends. Previously, it wasn't shared. You have C or D here, or function here, and you have another one in here. You can share this one, and by doing this, you will reduce the cost from 13 to 11. Or you could take C or D as a common factor, and you will end up with AB or AF, and this will even reduce the cost further to only 9. To generate the block diagram, we discussed this before. Just a quick exercise. You would say, I'll get A or B first. A and B. We get the OR first here, C or D. This is the C or D. This is the OR function. And then we get the other circuit based on the function G by doing more optimization as follows. You would say that G is equal to, you take the common factor A, and you will end up with B or F, C or D, or E. So now we have C or D here, and then we have B or F over here. And you add those three together by having this and A and the output of the first OR and the second OR. And after this, you OR it with E. And the cost will be reduced. Those kind of reductions, we call them transformations. The transformation can happen by using factoring or decomposition or substitution or elimination or extraction. So factoring means finding a factor from SOB or POS expressions. It's either going to be algebraic or Boolean. In the algebraic, no use of specific any specific to Boolean algebra, such as complement or idempotent, idempotent. In the Boolean, you use Boolean algebra. For the decompositions, you are expressing the function as a set of new functions. And the substitution, if you have two functions, you can take one of these functions and substitute it in the other. And the elimination, it's actually the inverse of the substitution. The extraction, it's a decomposition applied to multiple functions simultaneously. So we will take example for each one of them, starting by the algebraic factoring. So if you have f as you see here, you can see that we can take a factor from this part and this part, and we take a bar, c bar as a factor, you'll end up with b and b or d bar. So you can also do it step by step by taking the a bar first, and after this adding the c bar to it, or you just do it quickly. You take this factor from here and here, and the leftover is b or d bar. For the other two, you can take the ac as a factor, and you will end up with b or d bar. We calculated the cost in terms of g for each one of them, and you can see the reduction from 16 to 12. Also, you can factor based on the resulting b or d bar. So you take this as a factor, and you will end up with those two terms, a bar, c bar, or ac. And for these, you'll have the cost is equal to 10. As an exercise, how do we get this 10? You will count the literals first, 1, 2, 3, 4, 5, and 6. So you have 6 literals, and then you have 2 terms, that's 8. And you have those 2 terms, and the resulting value of g is going to be 10. In the decomposition, we can decompose f into e and h. We decompose f into e and h by saying we will consider this one to be e and the other part to be h. So f will be equal to e and it with h. And if you want to calculate g, you will count the number of literals, 1, 2, 3, 4, 5, 6, 7, and 8. And after that, you will add up the terms. You have 2 terms here, so g will be equal to 10. In the substitution, you can substitute one of them. Here we choose e into f. So we will have a bar, c bar multiplied or added with e, or ac added with e, and you will generate the same f. This is what we mean by the substitution. We made the substitution of e into f. So e here will be substituted here and here. And to calculate g, again, you calculate the number of literals first, 1, 2, 3, 4, 5, 6, 7, 8, and then you add those two to have g equal to 10. Notice that we didn't consider those two because it's only one literal. in each one of the terms. So you can see that the resulting cost here, they are all the same. As more transformation examples, if you have you are beginning with a new set of function x, y, and z, as you can see here. If you want to calculate the cost for this function, it's going to be the number of literal first, 1, 2, 3, 4, 5, 6, 7, 8, and then those two terms. We don't consider these because they have only one variable. And we will have g is equal to 10. In the elimination, you can do elimination of x and y from z. So you eliminate the x and y by having their value inside z. So there will be a bar, b or c, or c ended with a or b, which is the value of y. And you can distribute the a bar and the c to generate the z. And here you can see that the cost is increasing to 12. So now we are increasing the number of, we are increasing the cost, but we are gaining the advantage of having a two-level function, because right now it's a sum of product. The two-level optimization, if you do a two-level optimization of the function, the SOB form can help you to get the simplest possible implementation of Z. By using the kernel map, you can see here we have A bar B. So you fill the corresponding squares that correspond to A bar B, which is, this is A bar, and the B is constant right here. And this is A bar. So we fill this 1 and 1. Now finish this one. A bar C, this is A bar, and the C is constant here. So we make it 1 and 1. Notice the common one between those two terms. And we have AC, and that's the A is over here. And the C is constant here and here. So we have this 1 and 1. And the last one is BC. BC, the A is changing. So the BC is those two, which means this one and this one. And after this, you do the optimization by selecting those four together, and this will generate C, and those two together, and it will generate A bar B, and you OR them together to find Z. And you can see that the cost here is 1, 2, 3, and 4. So G is equal to 4. And this is the simplest form. If you had the function like this at the beginning, it might be difficult to fill the kernel map. But after we did the elimination, we reached to the SOB, and we've had a fairly easy way to fill the kernel map, and after this, do the two-level optimization. So the optimization can begin with any set of equations, not just with minterms or truth table. Increasing the gate input count, G, temporarily during a series of transformation can result in a final solution with a smaller G. Meaning, you start, for example, here with G is equal to 10. Sometimes it's good to expand it further, and you increase the cost, and then do the optimization, use kernel map to collapse this cost to the minimum possible, which is equal to 4. Now, for the extraction, if you are beginning with those two functions, A and H, and you can find the G, it's equal to 16. To do the extraction, you find a common factor and define it as a function. So you can see that there is a common factor between those two, which is, you can see if you take the A bar from here and here, you are left with B bar, and with D bar and BD. Similarly, if you take the C, you can end up with this and BD. So you can see that there is a common function between the E and H. So you find this common factor and you define a new function based on it. F is equal to B bar D bar or BD. And then we perform the extraction by expressing E and H in terms of this F that you just defined. So now the two functions will be three functions, F, which is this one that we just defined, and now E is going to be in a simpler form, A bar F, and the H is going to be CF. And this way we reduce the cost from 16 to only 10. And you can get the 10 by counting the literals first. 1, 2, 3, 4, 5, 6, 7, 8. And then you add those two terms. Notice that we don't consider a single term if it has a function with only a single term in the cost function. So the reduced cost G results from sharing of logic between the two different functions E and H. This is an example that includes many of the techniques for function minimization that we studied so far using CanoMap. It's a BCD, which we studied in a previous video, to 7-segment LED display decoder circuit. So the input will be the decimal digit from 0 to 9, and the output will be a display pattern in a 7-segment LED display. You can see there are 7 of them, 7 segments, A, B, C, D, E, F, and G. Also, there is a chip that have this 7-segment LED display, and you can see it has 5 pins in the top, 5 pins in the bottom, and this is our 7 segments, A, B, C, D, E, F, and G, with power supply and control pins, 3 more. And the job of the BCD to 7-segment LED display, if, for example, you have the input digit or the decimal digits that you want to show in the LED display is 0, you should light up those 6 segments corresponding to A, B, C, D, E, and F. For example, 7, you should light up A, B, and C. So to do this circuit, using the techniques that we studied, we have to generate the truth table. So the inputs will be in binary. You have 4 variables, A, B, C, D, and you generate this simply by 0, 1, 0, 1, 0, 1, and so on, 0, 0, 1, 1, and so on. The B is 0, 0, 0, 0, 1, 1, 1, 1, and so on. The A, you have 8 zeros, and the rest are ones. You can notice that you started only from 0 to 9. The other 6 codes, they will be considered don't cares. Now, for the LED or the segment A, this segment, For 0 input, it should be lighten up because it should light up because it's a 0 shape, and this segment here is lit up. Similarly for the B, C, D, E, and F. This is why we have all of them once, except G, it will be 0. If we take another example, for example, 3, you would say that I need to light up those LEDs, which corresponds to A, B, C, and D. This is why we have 1, 1, 1, 1, and the E and F will be 0, 0. The G will be 1, and so on. You can fill all the outputs. After you have the truth table filled, you can generate 7 Carnot maps for each one of these segments. So going back to the table, you will generate a Carnot map for A, for B, for C, for D, up to G. Each one of them have a separate K map. For A, the generated Carnot map is, as you can see here, we filled it based on what we have, what we had in the truth table. So going back quickly, you will have 1, 0, 1, 1. So you fill it like this, 1, 0, 1, 1. Going back again, 0, 1, 1, 1. You fill it here, 0, 1, 1, 1. And then you keep continuing. 1, 1, which is here, 1, 1. The rest of the n available codes, we will consider them to be don't care. And we will do this for all the segments. After that, you can use the selection rule that we studied and do the optimization for each one of those LEDs. For example, if we take D, you can see that we can have those 8 together, and this corresponds to A. We can have the this purple one. You can see this with those 2 as B bar C. We can have the light blue one as CD bar. We also can have the corners, which is the light green ones, as B bar, D bar. And we will be left over with this one. We will include it with the don't care to generate B, C bar, D. If you fill all the Carnot maps, you can see that there are some common terms. For example, the red one here is common between the A, D, F, and the G. The light blue one is common between the D, E, and G. This will help us when we draw the logic diagram. After you get all the functions based on the Carnot map simplifications, now you can draw the logic diagram. Before we go there, you see the common terms are shown in colors between the different segment functions. So for example, the light blue one, CD bar, is actually shown here in the D, in the E, also, and also in the G. Now, we rewrite those function here And based on these functions, we draw the block diagram. So for A, we have four terms, and this is why we have 4 inputs or gate at the end, and each one of them is A. You can see that we got the A directly, and C, we got the C from here, and then we generate an AND for the BD. This is B and D, and another AND for the B bar, D bar. This is B bar and D bar. And you can see that because B bar, D bar is shared among other segment functions like D and E, it's also taking for the D and E, as you can see in the block diagram. Now, to make the block diagram looks nice, you should start by drawing the inputs, which is A, B, C, and D, in their original form or normal form, and on their complements for, as you can see here. You will have sometimes, it's better for you to have multiple level, like for example, when we generated D, we already generated B, C bar here, and then we took the output and we included the D using another AND. So doing this, we could share the BC bar with other two functions like this one here in F and in G. And you can confirm for each function A, B, C, D, E, F, and G, the correct equation or the correct function is implemented using primitive gates. Now this A, B, C, D, E, and F, and G is connected to the LEDs to perform the BCD to 7-segment LED display decoder circuit. To show some example, we will show all the cases for all the numbers. So if we have 0, we will enter a binary value 0, 0, 0, 0, and it should light up like this. If we input 1, it will light up as you can see here. If we input 2, it will light up like that. If we input 3, it will light up as 3 in the display, and so on for 4, 5, 6, 7, and 8, and then if you input the number 9.